Hi all, please check the chat of Zoom.
Okay, good. What time is it right now? Good morning. No, not good morning. Good afternoon, I guess. Welcome back to our Statprob class. Today, I intend to finish up the material I owed last week, and then we are going to finish up the random variables chapter with expectation. There's not much material in expectation, so I expect, I made a joke right there. I expect to finish quite at least on time today. So let's just start, I guess. I was going to wait, but I think we can just start since most of you are here right now. So as usual, I'm going to ask you to turn on your cameras, at least for the beginning, so I don't feel like I'm speaking into the void. Hello, good afternoon. Who's here today? Oh, what's this? Bagus, it's just a black screen. What's up there? Oh, Jerome is in class. Alifiandra is somewhere in space. Oh, there you are, Bagus. I just saw a black screen just now. We have Abimanyu, we have Zahran with the same background as Bagus. Is that like a template for some event, perhaps, that all of you are using the same one? No? Just best friends? Okay, and then Ferdi is somewhere on Google Maps, I think. Did I guess it right? I don't know. I'm just making stuff up. Okay, Johannes is here too. No background to make fun of. Seto is here too. Thanks. And Altaj is, as usual, invisible because of the light behind him. Hi, Altaj. Can you shift just a little bit to your right so I can see your face? Hello. Okay. No, it's okay. Just for now. You can go back if you want later. Faras is also here. Oh, Faras must be a PMB committee because he has that particular background. Okay. So no one else? No one else want to keep me company? No girls? I have Yolanda and Hanifa here, but they're both maybe belum siap tampil kali ya. Oh no, there's Hanifa. Hello. Anyone else? No? Okay, there's still some people waiting in the waiting room. Give me a sec while I get to them and admit them in. So before we start, um, anything you would like to tell me? Maybe about homework, maybe about Why do you have to put a pre-test on the materials, ma'am? There's only 5 questions. I promise it won't take that long. Has everyone done the pre-test by now? I don't know. I haven't checked. To be very honest, I haven't checked. So nope. Something is up with my Chrome. It will not open. Damn it. Okay, let me stop sharing just for a bit till I can sort this Chrome issue up so I can see your scale. Let's see, scale. Oh, someone unmuted. Oh, no, it was unintentional. I got all excited for nothing. Okay, let's see. Pre-test. Actually, there are 23 attempts. So actually, most of you have done it. Thanks. That's great. There are some questions that were apparently easy. Everyone got right. And there were some that were not so easy. And it's difficult. I don't even remember which ones. Can I preview it? No, I can't preview it. What can I do? Why can't I try it? I'm not allowed to try the quiz. I don't know how to do it. Okay. Any feedback maybe while I figure this out about the pre-test? Was it easy? What was confusing? Anyone? Before I start calling out the ones that got 100. Anyone? No, really? Quiz, switch form to. Oh, actually, I saw the wrong one, apparently. I saw the pre-test week 3. So for week 5, actually, there's only 18 attempts. Sorry, wrong one. Okay. Anyone? No? Easy? Haven't gotten around to do it? Or I just clicked whatever because I just wanted to get it over with? I see some smiles here. Guilty as charged. Jerome and Bagus are smiling. Curigakan. Okay, so since not all of you have done it, I'm sorry, I clicked the wrong quiz just now. Since not all of you have done it, I'm gonna leave it be and until the end of the week, and we'll get to it maybe next week. Because I don't want to give out the answers if you haven't all done it. Okay, fair enough. Okay, so I once again not invite you, but those that would rather turn off their cameras may do so now. I just wanted to make sure you're here with me. But if you want to keep me company, it will be very much appreciated and you can leave it on. Okay, I'm gonna share my screen again. There we go. Okay, so last week we went into the material of random variables. So we're going to do a brief review on what we talked about this week, just to make sure that you still remember. And if I recall correctly, I have not finished the joint probability, and I promised to do that, to cover that with you in detail this week. So I'm going to do a short review on everything from the beginning, and then I'll go into more depth about the joint probabilities of random variables. Then we can go on to expectation. And I'll take a short break in the middle of that. So once again, we remember that random variables is a function that assigns a numerical value xs to each possible outcome of an experiment. So if I have my experiment outcomes, that's my Venn diagram, instead of denoting it as is, I map it to a certain number. So say we had, what samples did we have last week? We had like when I throw 2 dice, instead of denoting the output explicitly, such as, for example, my output of my first dice 1 and the second dice 7, instead of denoting it in detail, I only need to know what is the sum of the 2 dice, and then I could map it to a certain number. In the case of a sum, then it should be 8, right? But here in this particular graph, I show that every single dot on the Venn diagram is mapped to one number. But as we've seen last week, that's not always the case. If I were to want to define a random variable that computed the sum of 2 dice equals to 7, then I would have actually various outcomes. For example, here 1 and 6, the amount would be 7, right? I would also have 2 and 5 and so forth. And all of these I could map to a single value of 7. So here we recall some terms. If you recall injective function, a bijective function, a surjective function, please review those terms. But in this case, we know for a fact that it is not a one-to-one relationship. It's not a one-to-one mapping because I can map multiple outcomes to one single number. We also had 2 different types of random variables that we looked at. We looked at the ones that had discrete values and those that had continuous values. In order to describe these random variables, we looked at some functions that we can define that can describe how these variables are distributed, how these probabilities are distributed. We looked at first the PMF, which if I can remind you using a graph, I want to know the probability. This is my real number scale. I want to know the probability of my x, my random variable, to be a certain value, exactly this value. This is why we use an equal here. Sorry, exactly equal. Next, for my cumulative distribution functions, on my number scale, I don't need to know an exact number, but instead I want to know the probability of my random variable being a certain value up until x, so less and equal than. So the PMF and CDF can both be used to describe discrete random variables. Since we already decided that we have 2 different types of random variables, we have both the discrete ones and the continuous ones. Now we're going to look at how can we describe these continuous ones, because obviously if it's continuous, I wouldn't be able to determine the probability at one exact value. So for PMF, I can only use it for discrete. For CDF, I can also use it for discrete. But for CDF, I could actually also use it for a continuous variable. What else can I use to describe a continuous variable? I can also use a probability density function. So if I have my real number line again here, a probability density function can help me compute the probability of my random variable being between a value A and a value B. So the probability that it is here. Please distinguish this from the previously defined PMF, that is at a certain number, CDF, that is up to a certain number. And for PDF, I have both a left and right limit. How do we compute it? We use our little friend integral here. Last week's weekly reflection showed me that a bunch of you were apprehensive because this little guy came out. This little curly guy came out. So once again, I'm going to try to assure you that the point of Statprob is not to solve the integral, but for you to be able to translate the real world's phenomenon into the proper function, be it a probability density function, a PMF, or CDF. Do you need to solve it? Well, that's the ideal case, because by taking Statprob, we assume that you have already completed stat calculus, or at least you're taking it at the same time. So the relation between CDF and PDF, we can also determine it by using the integral. And what's the opposite of the integral? It is the derivative. So up until now was a brief review on the 3 types of functions that we can use to describe random variables. This is where I left off last week, which is the jointly distributed random variables. I'm going to take a break, not a break, just a small pause here to invite you to go to your chat in Zoom, and please write down your name, not your name, attending or present if you are present. And I'm going to take a small drink break while you write down your names. Does anyone recognize this name, Ali B? There's someone in the waiting room named Ali B, initials B, but I don't remember that name. Anyone? No? It's not an international class student? Don't think so, right? Okay. So no's, you're not coming in, mister. Okay. Okay. So this is where I left off. No, not Ali B as in alibi. No, Ali, I'll write it down. Ali B, initials like that. No, no, right? I don't recognize the name. So I wanted to cross-check with you guys if it's just me that doesn't recognize it. Okay. So last week, we stopped here. We have the general idea of what it means for jointly distributed random variables. So we already learned about correlation, because correlation is when we're trying to model the relation between 2 statistics, right? Because as you know, in the real world, nothing is actually like working on its own. The same goes for random variables. We sometimes also want to know how are they distributed together. So since we already learned about 3 different functions, PMF, CDF, and PDFs, we're also going to use these functions to define our jointly distributed random variables. So first is the PMF, which is same thing. I want to know when my, for X, it is exactly at a value AI, and at the same time, my Y is also at a certain value J. So we know, in this case, we know how they are distributed together. So I can only compute the probability of X with Y's condition known. So if I wanted to know the probability of X alone, I could deduce it from the joint probability, because when I'm talking about X equaling a certain number, I don't care about Y at all, but I have its information. So what I can do is, when I want to extract only the X, I can just sum up all of the probabilities of X, while X is that particular value, Xi, and for every possible value of Y. So here Y, so see, the iteration of the sigma here is on J. So that's the index that we used for Y. So Y can have any value as long as X is the one that we are looking for. Then we can sum it up. And conversely, that's the same when I want to extract the probability of Y. X can have any value as long as Y is equal to the desired value. What about CDF? It's the same case. I want to be able to compute the probability of X being under a certain value, while at the same time, Y is also under a certain value. And if I would want to extract X alone, then I can just sum up, not sum up, I can just find the probability of X under that intended value, and Y does not have to have an upper limit, or its upper limit is infinity. On the other hand, when I want to extract the distribution of Y, the X is the one that has no limit, or it has an upper limit of infinity. So based on this logic, we can define a CDF for a discrete RV as follows. If it's discrete, then I know, right? I want to know the probability up to a certain value. It's discrete, so I know the probabilities at every point below the particular value I'm looking for. So I can just sum up. Here you can see it's a basic summation using a sigma of all values lower than the particular value and lower to the particular value of Y. So as long as X is equal to any value under A and Y is equal to any value under B, I just sum them up all together. So now we are going to look into more detail on the example that I kind of skipped through very fast, very quickly last week. So we're going to define, I have 3 batteries. I have a bunch of batteries and I want to select 3. So I have 3 new batteries. These are 3 new brand new batteries. Then I have 4 old ones that still work. And finally, I have 5 that are old and don't work. So I have 5 old batteries. So from these options, I want to take 3 at random at the same time. I was asked as well in another class, at the same time or one by one, it doesn't really matter. But for the sake of argument, we say we're taking 3 at the same time. So if I want my random variables X and Y to denote, X is the number of new batteries chosen, and Y is the number of used but still working batteries, which is the blue ones, then how can we define the probability? You probably already looked through the slides and you see that this is usually denoted using a table because it's the easiest way to show them. So since I'm taking 3 batteries, the possibility of me, this is I, sorry, you can't really, so since I'm taking only 3 batteries, I denote the number of, sorry, this is X, and this is Y. X is the number of new batteries. If I take 3, it is possible for me to take all 3 of them being new, but it's also possible for me not to get any of the new ones. So I have 3 possibilities here. For Y, I'm taking the used but still working, which are these blue ones over here, and I could obtain 0, 2, 1, 2, or 3. So say I would want to compute the probability of me obtaining in my grab, I get 0 new batteries. Let me color code it so you don't get confused. So if I want to compute the probability of obtaining 0 new batteries and 0 old but working batteries, I would need to obtain a permutation slash combination of these 3 objects to calculate what my probability is. Now, I'm going to intentionally not tell you what I need to use to find that, because I'll just leave that as a little mini quiz for you to figure out. I need to use, the hint is it's either permutation or combination. So if I have 0 new and 0 black and 0 blue, let's just say that, that means that I would have to obtain, I would have to take among these, right? Among the red ones. If I'm going to compute the probability, note that my sample space, which is underneath here, it's the part on the denominator, would be my sample space, which is, I need to get a combination out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of 3 out of 12. So among my 12 batteries, I'm taking 3. This is my sample space because I want to take 3 out of all 12. But my favorable event is based on the x and y. When x is 0 and y is 0, thus it must be red. So I'm going to leave that to you to compute all of these functions. The actual answer is already given to you, so you can check if you use the wrong method. So it is already pre-computed for us. It is from this book that, by the way, does anyone have yet? I thought so. No, no one? Not even online? I'm not supposed to endorse that, but really? Please find it out. There are a bunch of exercises that I use in my materials from that book, which hint probably means I take stuff for my exams from there as well. So after we compute all of them, this is the precise value. So like this one is the probability when x equals 0 and y equals 0, or I can write it as a joint probability p 0 and 0, where this one here is the probability when x equals 0 and y equals 3, and so forth. So if I were to ask you, what is F11? That means I'm asking you to compute. Note that this is F and not P. F is a cumulative distribution function, right? So I want to know what the probability is that X is less than and equal to 1, while Y is less than and equal to 1. And here, this is a simple P. So I want to ask you what what's the probability of P equals Y equals 2, X equals, I don't care, all of the X's, and Y equals 2. From the graph, it is straightforward. I should have used a different color, sorry. I'll redo it with a different color. So first, for the first one, A, I want to know when P is, X is less than 1. X less than 1, that means it could be 0, it could be 1. Y is less than 1, that means it could be 0 and it could be 1. That means I'm considering all of the combinations where y or x are less and equal to 1 or equal to 0 or 1. What do I do with these four informations? I just sum them up. 60 plus 40, 100, 140. They will give me 140 over 220. And for the second one, when I'm trying to compute y equals 2, that means I don't care about the value of x. So any value of x is possible as long as y is equal to 2. That means I'm considering all four of these probabilities. And 0, I just don't sum it up. We already have the sum of them here. And then we can obtain the answer for 8 over 220. Seems simple because we've only been talking about the discrete ones. So if I recall, last week I said, ooh, this is a bit complex. Please wait for me until I can explain it to you in more detail. This is what we're going to do now. So just now we had discrete values of probabilities here of every single possible value of x and every single possible value of y. But we don't have that when we're talking about a continuous random variable. Instead, we have a function that will tell us what the probability is between a left limit and a right limit, or a bottom limit and a upper limit. So if I already knew that for my x, I have the limit a and b for my x. This is the probability of x, p, a, x, b. This is the definition of PDF. Don't get scared. We already looked at this before. And I know that I also have the probability between c and d for my y. This is defined for x, and this is defined for, y. If I would want to join them together, they are both integrals. What can I do? I can have a double integral. Note that here, my probability of x is between a and b. And although I write it first here in front, here it's the second one. Why? Because this is the integral of x, which result I then integrate it, sorry. This is the integration of x, which after I have the result, then I integrate it over y. This is calculus, Statprob, so I'm not going to go into detail as to why the orders are as such. Let's look let's look into more detail how we can use it in a real question. But before, we need to define the CDF. As you recall, PMFs and CDFs can be used for discrete random variables. PDFs are exclusively for continuous random variables, but the CDF can be used to define continuous random variables as well. So by definition, when I have this is the CDF of two random variables x and y, which are under a and b, I have this definition here. We already looked at this. But if I only have the PDF, I need to be able to translate it up. So this is CDF, up until a certain value, But what happens if I have a PDF that gives me two limits, left and right? Then I just simply need to define the lower limit as negative infinity. We still have our double integrals, and the limits are adjusted accordingly. So here my x upper limit is a. So here my x upper limit is a, and my y upper limit is b. So here I have my y upper limit is b, but the bottom limit are both negative infinity. I have to admit to you guys, the first time when I was studying Statprob, that negative infinity scared me a little bit. But don't worry, it's not really that complicated. Let's look at this example here. So the joint density function. So here we have PDF. Don't forget that sometimes density function leaves off the P. Cumulative distribution function also leaves off the C, and the PMF also sometimes leaves off the P. So be careful of that. So I would want to know what is the probability of P being over 1 and Y being less than 1. I only have one limit here. But what I have in my information is the density function, which defines both the upper and lower limits. So let's first translate this into a statement that has both limits. So for my X, I want to compute it. Sorry, that's not right. Let's redo that. So for my X, I want to compute for X being larger than 1. That's right, right? Yes. And less than infinity. While for Y, I want to compute its probability being less than 1 and larger than negative infinity. So if I were to translate it into my density function, I can compute its integral, which is, first, I need to write the function like this. And I first integrate it against X. Since I'm integrating it against X, my limits of my integrals would be 1 and infinity. Next, I need to double integrate it. So now I'm going to integrate again the result over Y, and the integral limits would be the limits of Y. So this is negative infinity and 1. Looks too complex, miss. We have so many infinities here. We need to redefine it a little bit. Look at my PDF. It is the function is defined for a certain interval. So it's defined when X is over 0 and up to infinity, as well as Y, which is over 0 and larger than infinity. Thus, if I have, for this one, this particular, the first integral of Y, it goes down until negative infinity. I don't need to compute the integral up until negative infinity because my function itself is not defined based on this 2e to the power of negative x lower than 0. So here I can replace the bottom limit using 0 because this particular equation, this particular equation 2e to the power of negative x minus 2y. I wrote it down wrong, didn't I? This is e to the power of negative 2y. E to the power of negative 2y. So this function is defined only up until the bottom limit of 0 anyway, so I can just change the bottom limit to 0 as well. The upper limit doesn't change, it is still 1. This is the y limits. What about the x? X has a bottom limit of 1, which is defined in my function, but the upper limit goes to infinity, and actually my function is valid up until infinity. So I can't change that one. We have infinity here. It looks really complex, doesn't it? But up until this point here, your job in Statprob is done because you need to translate this PDF into how you can use it to compute a probability. So up until here, you're halfway done. You will get half of your points already. If you're interested on how to continue the derivation, up until the final form, please recall that when you are integrating over x, you don't have to think about y, because when you're integrating x, y is a coefficient. So you can just take it out. So if I were to continue this, then when I'm integrating x, I just need e to the power of dx dx. My 2e to the power of negative 2y will be processed later, and so forth. I've already taken the liberty to give you the solution. You can find these on your slides as well. How does this come from here to here? That's calculus. So don't worry, don't forget that e to the power of anything is integrated and or derived into itself. So e to the power of 1 integrated is e to the power of 1. So it's not that complex. You just need to remember some integration rules. The same goes for the second one. When I'm trying to compute the cumulative probability of A, so for I want to compute the probability of x being less than a. See, we have the subscript of x. Y does not matter to me. So it can have any value. So technically, y that I want to compute is between negative infinity to infinity. But since my function does not define y under the value of 0, I can replace the bottom limit with 0. And then we have this equation here. Even this key stops here because the Statprob section is done here. Too long didn't read. For the jointly distributed random variables, we can define the joint PMF as follows, joint CDF as follows, joint PDF as follows. Brief pause. Any questions? Drink break for me. Let me check the chat room. Some people write their questions here. No, not yet. Don't worry, I'll give you a chance. Maybe it hasn't come to you yet. No? Can I continue? You won't get mad at me? Okay, so I asked you to read this part independently. Haha, independent random variables, read them independently. Too long didn't read version is the random variables can be independent if I were to compute the joint probability and it equals the multiplication of their individual probabilities. So if we compute the joint one and we compute the multiplication of the singular ones or the independent ones, if they are the same value, then I can say that they're independent. Anything other than being equal, then they are not independent. As simple as that. As you also probably also looked at in the previous chapter, if it equals to what it is, it equals to that based on the hypothesis, then we can say they're independent. If it doesn't equal to that, then they're not independent. That is the main point of the independent random variable. As a closing, I want to introduce the conditional distribution. We're not going to go into much detail because it's the same thing that what we learned in conditional probability. The only difference is that we're no longer talking about singular variables, singular outcomes, but we're talking about random variables. Remember this friend here? I asked you very kindly to do not forget me. This is a very important equation that we're going to use so many times. We have the probability of E given F, which is defined as the fraction of the joint probability, not joint, sorry, the probability of the intersection over the probability of the conditioning event. It is the exact same thing if we have discrete random variables, both discrete and continuous. If I translate this particular equation into a discrete random variable, what do I have? The probability of x given y is the fraction of the joint probability of x and y. Correlated, right? This is the joint probability, and previously we had the intersection over the probability of the conditioning variable. Same thing. We have the rule that we're not supposed to do this dosa besar. It cannot be equal to 0. For continuous random variables, it is the same thing, but it is defined as an integral because we're using the probability density function. Once again, too long didn't read version. For a discrete random variable, we use discrete joint probabilities. For continuous random variable, we use the continuous joint probabilities, and it just follows the same pattern that we already looked at in conditional probabilities. Any questions? Any questions? I'm going to ask the questions then. Ferdi, are you drinking coffee?
Yes, I am.
See, it's not a difficult question. I just had a question. Anyone else? Any questions? Okay, so I believe you probably need some time to internalize. So at my clock says 14:22. So I'm going to take maybe 4 minutes break because I don't know, you guys preferred, you're the class that preferred a brief break, right? Or was that the other class? I mixed up everyone now. Okay, so 4 minutes brief break. Go get your refill of coffee or whatever, and we're going to continue with expectation after the break. See you in a bit. Okay, sorry for the longer than expected break. There was a delivery courier coming to my house and I had to go out and take it. Okay, so we're going to continue with expectation. It is not very complex, I promise you. As long as you have grasped the concept of random variables and how we can define them, you should find this section a little bit easier and quicker to understand. It's okay, Jerome. I like that filter. Why did you turn it on?
Oh, I was playing around with when it was break. Sorry.
No, don't worry. It's okay. I just noticed it. Okay. I know what Among Us 2 is.
Oh, okay.
Okay. So we're going to talk about expectation. So remember the joke I tried to make at the beginning? I said, I expect not to take too long. I expect to finish by 3 o'clock. I expect I expect it to rain today, for example. So you guys probably already know what we are getting to with the word expect. So as we mentioned, when I'm trying to map outcomes to a number, that's the process of defining a random variable. So now I no longer have outcomes that are defined specifically, but I have a series of numbers that tells me something about the outcome of my experience. So if I have a bunch of numbers that should come out, then I should also be able to have a certain expected number or expectation or the average, the mean, or in Indonesian, what's my hope, what's my harapan, what do I expect is going to come up? And in order to compute that, we have a particular, not statistic, metric that we can compute, which is expectation, which we also write as E, and then we have the, what is kurung siku in English? Anyone?
Square brackets, Miss.
Square, oh yes, oh my God, square brackets. We write it as such, and that is the representative number that we use to say, if I have a random variable X, what value do I expect to come up? A visualization is as such. So when I have a PMF, and for example, I have a PMF of X equaling 2, 0.1, equaling 3, 0.7, and the probability of X being 4 is 0.2. I only have the possibility of my random variable to be 2, 3, and 4. There's 3 possible values that it can take on. So if I think of my EX or my expected value, you could possibly say that I expect it to be somewhere near 3, right? Because that's the highest probability. Or the other way to think about it is that how can I balance this bar over here? What is my center of gravity? So if I were to balance my balance beam, I would probably need to put my axis there. Why? Because if I put it in the middle, then it will be heavy to the right. If I put it to the left, then it'll still be heavy to the right. So I need to find that exact sweet spot that determines the middle of my distribution. And this is my expectation. How can I compute it? You only need to know this one slide. In order to compute the expectation of a discrete random variable, I can use this Px equals the value. Don't forget, when I'm saying exactly equal to, that means I'm talking about the PMF. And for here, for a continuous random variable, then I need to use the PDF between limits negative infinity to infinity. It's not just the integral of that, but see here that I times it, I multiply it with the x itself, as well as here, I multiply it with the x itself. This is the basic equation. Now we're going to try to compute it. So I want you to please compute the expectation if I have a random variable x. Don't forget the first step of doing any random variable question is to define the random variable itself. So here I have to define x is the outcome of rolling a die. And if I were to compute it, do you remember what possible outcomes that I have? I have 1, 2, 3, 4, 5, and 6. I have one die, and what possible outcomes do I have? Do you remember what is the probability? If I have the outcome of rolling die as such, then what's the probability of my x equaling 1? Don't forget.
1/6.
Yes, I have fair written here, so I can assume it's 1/6. Same goes for x equals 2, 1/6, and so forth. So using this expectation equation, I can compute the expectation of x being the sum of I, where I equals 1 until 6, for xi, p, x equals xi, or sum I equals 6. Sorry, shouldn't write the sigma anymore. Or 1, probability of 1, plus 2, probability of 2, plus 3, probability of 3, until 6, for multiplied by the probability of 6. This is for every single possible outcome that I can have. Just trust me, and I already computed it for you. So the expectation is 7/2, or this is 3.5, right? 3.5. So keep in mind that before we had a probability, so if I want to illustrate it using that balanced beam that I had before, so I have here, this is 1, 2, this is 3, this is 4, this is 5, and this is 6. This is the probability of my random variable being 1, being 2, and so forth. All of them have the same probability, which is 1/6. If I want to take the center of gravity to balance this beam, then it makes a lot of sense, right, for me to put it right here, which corresponds correctly with the computed expectation. Example 2. I'll give you some time to read it through and maybe reminisce about UI train station and the commuter line. Probably haven't been on a train since March. I haven't been. So I'll give you some time to read it, and I hope you haven't forgotten what a commuter line is. Okay, so we have a random variable x, which is the number of hours of delay of the commuter line. So let's say here we have random variable x. Don't forget to always define the random variable. X is the delay in hours. And I have the definition of x based on this PDF here. Now I want to compute the expectation. What's the average time? What is the expected time? What is the mean time that you usually need to wait until the train comes? So we can compute the expectation as such. So the expectation of x is integral over minus infinity to infinity times my x times my function over x. We need to redefine the limits because my function e to the power of negative x is not valid from the range negative infinity to infinity. Instead, it's valid for my e from larger than 0, so any x. So the upper limit can still stay infinity, but the bottom limit must change to 0. Let's actually try to solve this one. I don't think it looks that complex. It would equal to, anyone? I just need to do this, right? I need to integrate it. What's the integration of x?
X squared over half.
Once again, x over
X squared over half.
x squared over half, right? Okay, and what is the integration of ex? Sorry, e
EX.
negative. Bagus, this is a trick question. You said the people told me that you are the calculus nerd in this class, right? You remember partial, no, was it partial integrals?
Yes, it's partial integration.
Because here we have a function x, and here we have e with the power of that function. You know what? Even I forgot about that. So guys, please brush up on your calculus. Up until here, your job in Statprob is done. You have translated correctly, but it is the ideal outcome if you can integrate it fully, because in this particular question, I'm asking you a particular number, right? What's the time that you need to wait for the train? Please check if my answer is correct here. So here it says that the integration is 1, because it's, as Bagus said before, it's a partial integral. So I need to read up on that again too, before I can go through it, the steps with you guys. So based on this equation here, we know that we have to wait for 1 hour for the commuter line at UI train station. Doesn't really make sense because I don't think you usually need to wait for one hour. It's just for the sake of argument. So after we compute our expected value, you need to know that the expected value itself has some properties. So if I'm computing the expected value of a linear combination of random variable x, see here I multiply with a scalar value a, and I added it with a real number. I can then extract the a and b out, and I obtain a linear relationship. So since it's a linear relationship, I can also distribute a multiplication outside of it, as well as the expectation of a real number. This is just terminology. So when you're computing the expectation EX, then you can also say that you're computing the mean or the first moment. So I'm not really going to go that much into detail here, but statistical moments start from mean to standard deviation to skewness and so forth. So the first moment is the mean. And since the expectation describes a middle value or the average value, then we take the expectation as the first moment or the mean of random variable x. So if I want to have a power of the moment, I can also compute, if I were to be so inclined, to compute the expectation of power of x. So not only, so previously we had ex, now I want to add a power to it. What changes? The only thing that changes is that the multiplier of x is, I raise it to the power of n itself. Don't be too afraid. This equation is still the same with the previous equation for expectation as well as this one for continuous ones, but I only add a power of n. Another result that comes up from the expected value of expected value of any random variables is that if I were to compute the expectation of a sum of two random variables, I could compute them separately and add them up. And if I were to generalize it, it's not only for x and y, but for not only for two, but for infinity number of random variables. If I want to compute the expectation of a sum of all of them, I could also compute the sum of the expectation. So as to recap, the expectation is what we want when we're talking about what is the main representative of that particular, what value is the main representative of that random variable. But what exactly does it tell you? It tells you the mean. Remember the first time we met, the first week, we already looked at measures of central tendency, right? It doesn't tell us though about how many values I have. I only know that, oh, if I have this random variable, I expect 3.5 to come up here in the middle. I do not know how far it goes that way, how far it goes that way. So just like what we already learned in the first slide, the first chapter, it's not enough to compute the expectation only, because these three random variables, z, y, and w, all of them have an expectation of 0. But as you can see, they all have very different values. So just like what we learned in the first chapter, we also need a measure of variance in order for us to visualize and understand more about the random variable itself. What can we compute? You remember what do we have for measures of variance? We have variance itself. Here we go. If x is a random variable, we can compute the variation or the variance by using the expectation. So all of it comes back to the expectation. Don't forget that there is a relationship between variance and standard deviation. Once you have computed variation, you can just simply take the root, the square root of it, and you can obtain the standard deviation. Yes. So for an example, we are going to try to compute the variation itself. As I already mentioned, in order to compute variation, we can compute it using the expectation. So in our previous example, we computed the outcomes of the rolling of a fair die. So X is the outcome when we roll a fair die, which I can also write 1, 2, 3, 4, 5, 6. We also already saw that the expected value is 7/2 or 3.5. So if I were to ask you to please compute the variance, what can I do here? I can just simply compute the expectation of x squared and expectation, the expectation value to squared. So here I already know this is 7/2 squared. This one I do not know yet. Remember, the expectation of x squared is the second moment. So here I need to pre-compute it first, right? So I need to compute E that, which is basically 1 powered times the probability of 1 plus 2 squared to the probability of 2 plus 3 squared to the probability of 3, and so forth until 6. I have already pre-computed it, and I have computed it to be 91/6. You can check with your calculator in case I made an error, but then I can input that to this here, and we can obtain some number that I don't remember. Let's see. So here we computed first the second moment of the expectation, and then we can input it to the variance equation, and we obtain the variance of the random variable as follows. Obviously, when we compute the variance, it brings us some important properties or requirements of the variance. So for any constants a and b, I can compute the linear combination of ax plus b as follows, and so forth. Next, we have covariance, not variance. Be careful. Why do we need to learn about the covariance? Because we looked at joint random variables as well. So when I'm talking about variance, I'm only talking about the spread of variables x or the spread of variables y. But since we now know that random variables x and y can actually be computed together with a joint probability, then I also need to be able to compute the covariance. And it can be computed once again using the expectation. Don't be too afraid. This is just expectation of singular random variables, and this is the expectation of both. You can also compute it using the means as follows. As a result, we also obtain some properties of the covariance. What is their relationship between covariance and variance? What is, the fact that covariance xy will, xy will equal the covariance of yx. They are both interchangeable. The multiplication can be put out, and so forth. Between variance and covariance can also be computed by the variance of each random variable. So in order to compute the variance of the sum of both, I can compute it as follows. So variance of x plus y, I can add up the variance of the individual random variables plus 2 times the covariance. So up until now, you've seen the equations. How can I compute covariance? But I haven't actually told you what it means yet. So we know that a covariance is trying to describe the variance of 2 random variables that can be computed jointly. So it shows me the linear relationshipness. That's not really a word, but I didn't find a better way to describe it. The linear relationshipness between 2 variables. So like if x is going this way, is wider, what happens to y? And the other way around. What is the linear relationship between the two? So if I have a covariance of 0, it means that they are uncorrelated and they do not have a linear relationship. So y will not grow with x or shrink with x, and the other way around. But be careful, we also already looked at what it means to have an independent random variable. Uncorrelated does not mean independent. Remember, when we're computing independent random variables, we need to fulfill a certain rule. So the probability of the joint must equal the multiplication of the individual probabilities. That is your go-to when you're talking about independence. But for correlation and independence, they do not mean, they do not automatically mean the same thing. If they are independent, then they are uncorrelated, but not the other way around. So if you need to prove the relationship between x and y, and you have proven independence, that means you can prove that they are uncorrelated. But if you have proven they are uncorrelated, does not mean that they are independent. Sorry. As I just mentioned, independence then correlation, but not the other way around. And since correlation is a very closely linked to covariance, then I can also deduce that if they are independent, then the covariance is 0. And once again, it does not work the other way around. And as a consequence, since the covariance is 0, if you recall, the variance of x plus y should be the sum of x and y plus covariance. So if the covariance is 0, then I don't need to add that up anyway, and the variance of x plus y can be computed simply by the sum of the variance of each random variable. I can then generalize it as well to more than 2 random variables. Lastly, if you recall chapter 2 of correlation, there were multiple equations that you could use to compute correlation. The first, you could use raw values. You could also use z-scores. You could use, what else could you use? You could use z-scores, you could use raw values, you could use ranking values. And one more, you could also use covariance. But I recall that in the slides of that chapter, I said, stay tuned for covariance because you've actually not looked at it yet. I just gave you the equation, how to compute correlation from covariance. But now, since we've already covered covariance, now I can clarify to you what I meant in the chapter 2. So if you're going to compute correlation, you can use the information of covariance. The correlation can then be computed using the covariance over a square root of the multiple of their variance. If you looked at the equation in chapter 2, you probably didn't know what it meant yet, but hopefully now it's clear since we've already looked at random variables. Yay, that's it. As I mentioned, expectation is not that much, actually. You just need to know that expectation describes the midpoint and variance and covariance describes the distribution. I'm going to stop here. And for once, I have caught up with the material. Usually I always have I owe you something at the end of the class, but thankfully I have caught up now. And I'm going to use the last 6 minutes of class until 3 o'clock, no, 5 minutes now, to open a question and answer session. Any questions? If it's about homework, please direct it at Skele. I'll ask the assistants to get back to you. Other than that, any questions? It doesn't have to be about the material if you're a little overwhelmed. I have no questions, I just don't get it, don't worry. But maybe you want to ask any other questions. Oh, homework 1 solution. Okay, I will ask, I have it, but since it was compiled by the assistants, I'm going to ask their permission first. And I don't see a problem to share the homework 1 solution. I'll coordinate that with the assistants first. Anything else? You can use the chat box if you're too embarrassed to unmute your microphone. Homework 1 solution. I'll share it after I'm confirming with the assistants. Anything else? Homework 2 solutions. No, I will not give it to you because the deadline has not passed. Anything else? Oh, for the exercises of last week, I told you I would upload the solutions, but apparently when I saw the key that I wrote, it was handwritten, and I don't think you can really read my handwriting. So let me retype it so it's easier to read. Then I'll upload the solutions of last week's exercises. Did you notice that today's pre-quiz, pre-test, had 1 question that came from last week's exercise? So if you did the exercise, it should not be a problem to fill in the pre-test. about activities in class, there was a question in private to me. Do I have to do the exercise? Well, to be very frank, you do not have to. The exercises that I give during the activities, you don't have to. Like, I'm not going to put a gun to your head or anything, but the intention of releasing extra exercises or other activities is for you to be able to follow the slides and the materials easier. Because if I just give you the slides, I'm afraid that it'll be just a bunch of equations and bunch of integrals, and you'll get even scared. So please do it for your own benefit, and it will also hopefully give you a good idea on what type of questions that will come out in a quiz coming up sometime, and as well as for the midterms. Any questions? Maybe about the quiz I just mentioned, or maybe about the midterm.
I just have a question.
Yes. Oh, who's talking?
Jerome.
Oh, okay.
So I noticed there's this wiki page thingy, collaborative wiki page.
Oh, yes.
Mm-hmm. I still have no idea what we should do about it.
Okay, I'll show it to you. So to be very honest, I'm trying out different features of Skele because I don't want to bore you if we do discussion forums and then exercises again and again. So I am trying out some features. So that's my intention of using the wiki page. So can you see my screen, my Skele screen?
Yes.
Yes. Okay. So what I intend to do is, so where is it? This one, right? So you can click the random variables and expectation questions here, and you can edit this wiki page. And then I want each of you to add one question that you made yourself, a multiple choice question with 4 possible answers about random variables or expectation. So you can treat it as maybe a study guide or a cheat sheet, if you will. So you can look at each other's questions, and depending, I can use those questions for future quizzes, or maybe not for the exam, but for future exercises or future quizzes. If you want to see an example, I can show the one in the Statprob regular class. So it's the same activity as well this week. So as you can see, they have already started editing it, and we have a bunch of questions as a collection for self-study. If you're interested, I can also cross-share the questions from the other class. Although they're in Indonesian, if I do use them for this class, I will be translating them first, obviously. Does that answer your question, Jerome?
Yes. And lastly, is it like mandatory, or is it do we have to do it like each of us one question?
Once again, it's the activity in class. So
Right.
so we are, since I always conduct one sync class as well as a week long asynchronous class. So that is the activity of your asynchronous class, and I will recap it. So if you don't participate, it will count to your participation score, but I will not score them like on correctness or anything else. It's more to help you follow the class better.
I see. Okay. Thank you.
Anything else? Anyone else? I like this class. There's not much of you, so I can remember your names better. The other class has 65 people, and there's no way I'm gonna remember everyone. Anyone else? Maybe Altaj, that has the light in his behind him. Sadam, maybe have any questions? I'm just calling on names. Faraz, probably thinking about PMB right now. That's Faraz, right? Trying to remember, you guys.
Yes.
Any other questions? No, no questions? Okay, once again, I want to remind you that on Skele, we have a discussion forum every week. I may not post a formal discussion, but if you have any questions, you are welcome to make a thread at any time. Oh, oops, sorry. One more thing before before I close the class. I just remembered. I have something that I need to communicate from the secretariat and Budina. So I'm going to open this now. So I have been asked to release this feedback form. If you recall, usually in class midterm, you would get out. I would give out some papers for teaching evaluation, but since we can't do that, we're going to do it online. And I'm going to note the activity completion. And if you don't fill this in, you won't be able to access the midterm files. I just opened it now because I wanted to tell you guys about it first. Okay, that's it. Any questions? Not yet. A bunch of them, but a bunch of them about the materials. Okay, then. For once, we can finish roughly on time. And thank you all for your attention. Oh, wait, let me stop the recording.